you could produce the interference fringes. You could produce, okay, as long as the light source has coherence. All right, so let's look at this interferometer. Let's look at this interferometer. We call this head-interior fringes. Okay, if I have a piece of glass, for example, and then this is the some dark background theme, then you can have the reflection from these two surfaces. Okay, they're just like okay. Let me give everybody some microscope slides. If you just look at this, the microscope slides, this is the glass slides. There are two surfaces associated with them. Okay, this is the microscope slides. Okay, you see two surfaces. Does anybody see any interference fringes? Perhaps you can see my fingerprint, but not quite the interference fringes. Right? Okay, so this is exactly the setup like this. And then you can put it on your table to mimic the black background. But currently, the light is split by this microscope slides, and there's a front surface and back surface. If the light has enough coherence, then again, this is a light source going this direction, and then come down and pick up the interference fringes up here. So this is something like you try to look at the interference fringes. And this is called hand-interior fringes. If you have a lens to sort of to generate fringes on the screen, but you don't need the lens for this experiment because your eyes are good lenses. Okay. So basically, this is another scheme to have two surfaces to do interference, and then we have another setup called visual interferometer. Visual interferometer is like this. This is transparent glass. This is transparent glass. So you have two like this, and put it with the angle. With the angle. So the optic path difference along this direction is a function of x. This d is a function of x because this is a wedge like this. Okay, and you try to see interference fringes from top. And this is called the visual interferometer. But for example, if I review one here, review another one here, and usually for optical surfaces, you don't want to put your fingerprint on it. You take it like this. On the gauge, and yeah, and then you can construct a visual interferometer. Let's see how many of the pieces do I have. I think I have one more piece, and maybe first I'll give it to you, start the ruler, and then you guys can borrow from each other. So you can construct this visual interferometer, and because the optical path difference varies along this direction, okay, and so the optic path is given by this dx. That is a function of the x. If you move this along this direction, the thickness becomes thicker. Okay, so we can calculate the bright fringe or dark fringe is viewed from this direction. So if I have this d value as x, then this this optic phase is given by this, but don't forget that there's internal refraction, there's an external refraction. We are using these two surfaces, not quite using these two surfaces, not quite using these two surfaces. The two surfaces is these two. Okay. The reason is that when I just give you one slice, you don't see anything, right? So the experiment failed. But now, if you just put them together, and if this path difference is within the coherent length, you could start to see fringes. So you could try it. And then, in fact, I was thinking that I should set this as a quiz for today. So you can have some credit from this experiment. Anyway, so if you this is the internal refraction, this is the external refraction, but there's a pi phase shift right here. Okay, so then you can calculate the bright fringes according to this formula. If the phase difference is integer multiple to pi, then you identify the location where the location xm where you can see bright fringes, and you can also do the calculation for the m's mix-up fringes occur at this location. What was this thickness? Okay, so basically every time the thickness change half wavelength, you have repeat the bright fringes, okay? Because one long trip is going to be one wavelength, okay? So this is how you determine the location of the bright fringes according to this, and then deduce the optic path difference. All right. So this is the one interferometer, and another kind of similar interferometer is called Newton's ring. Well, I know that you struggle a little bit on the experiment, but I will come back to help you to do that. Well, another similar kind of interferometer is called Newton's ring. If you have a lens, have a lens like this, there's a curved surface associated with it. Okay, there's a curved surface associated with it. So you start to see that this is very similar to the visual interferometer, with optic path difference vary with the distance from the center of the lens. So if you just put it here, and then view through this, and if the light source has enough coherence, you start to see beautiful rings from top. And that is how people determine how good this lens has been polished. Because if the polish is not good, you see distorted rings. Okay, if the surface of the lens is perfect spherical surface, then you're going to see perfect circles one by one from this top. Okay, and if you have a reflected surface, can you see in the Newton's ring? Well, if you just look at the geometry, you can calculate the thickness of this. Okay, and this thickness is relevant to the radial curvature of this surface. So this calculation is also quite straightforward. You just calculate the x position relative to the radial curvature, x position relative to this radial curvature, and the thickness d determines the optic path difference. So you start to have this, and then you can determine the location of the bright rings through this calculation. Okay, this calculation is quite straightforward. Just from the trigonometry, you end up having the location of the bright fringes. All right, and then you notice that hey, I give you so many materials. The microscope slides, I give you a lens, but you don't quite see interference fringes. Why?
Because white light has small coherent lens.
Yes, because white light that has very small coherent lens and you don't quite see it. Okay. Unfortunately, today I don't have a filter. If I use for example, some color filter, then it's possible that you will see the Newton's ring. Okay, so just put the color filter to narrow down the spectrum of this guy. Then you'll be able to see the Newton's ring. Okay, but still that you see this interference fringes every day, every rainy day when you walk on the street. Why? That's from the sunlight. Sunlight is also has very short coherent length. That is because the film is very small. Okay, on the order of like micron. So the coherent length for the sunlight is very small, and you can calculate the coherent length based on this calculation. If you know the spectral line width for the sunlight, expand it over 400 nanometer to 700 nanometer, you can calculate this delta F, and then you can calculate this coherent length. And then you need to make sure that this film thickness is shorter than the coherent length of the light source. And then you start to see this. All right, so now, if you have two microscope slides in your hand, for one, the thickness of this is too big for white light interference. Okay, the thickness of this is like 2 millimeters, so you don't see any interference fringes from these two surfaces. But if you have two, and you put them together to create a very thin air gap between them, and then use your finger, squeeze it a little bit, and then you try to see the interference fringes. If you see it, let me know. I give you some extra credit from this course. Try it out. And then that is going to be interesting to experience that you see some white light interference. Squeeze it. Remember the air gap has to be very small. And then perhaps you want to view it through some angle. And if you struggle a little bit and still cannot get it, and you can pass the glass to the other people who don't have the glass. In fact, I don't have another pair of glass. Clean on the surface a little bit and then try it out. Squeeze it, but don't break it. The teacher assistant gave me the one glass slide like this, but there's some scotch tape on it, and then because of thickness of the scotch tape is too thick, so you cannot see the interference. Does anybody see the interference fringe? View it from some angle. then push a little bit. No parecer. But if you push a little bit, basically you create something similar to Newton's ring. Okay, if you push your finger along this direction, you create something like Newton's ring. No luck. Now you change, you have to use a finger to push a little bit up and down. Okay. You will see it for sure. Pushing is two fingers push at the center. And then of course you can clean up the surface first. If you can sort of clean it a little bit. And that is quite often how you did lithography in the clean room. When you enter a clean room to do lithography, you want to put your photo mask on your wafer. How do you know your photo mask is well attached to your wafer? Well, if you see the interference fringes.
Yeah.
Aha, somebody has seen it.
It's not the edge of his head.
You're very bold.
We'll see from this direction.
Maybe come here. Maybe you come here. Maybe come here.
We can come here and see this.
All right. If you see it, then you go buy a lottery. Squeeze, and then you see the fringes start to move. Sometimes you need to view from an angle. That is easier to see. You view from an angle. It's a beautiful fringe. They are beautiful fringes.
Well, I can see it now.
Oh, wow. So you'll be admitted to the College of Semiconductor. So next time when you enter the clean room to do your lithography, then all right, more or less everybody's lawyer. But you can still keep that and then play with that. Wire interference is very difficult to perform, especially if you want to use microscope from here. Well, the physical distance from here to here is about 1 foot, about 30 centimeter, or 10, 20 centimeter. And then you have to adjust the path difference down to micron precision to see wire interference here. Okay, in my life I saw like perhaps two, three times, but then use two microscope slides. You can see it after a little bit struggle. Okay, as long as the air gap is small compared with the coherent length, and then I do encourage you to do a calculation to determine the coherent length of the white light. It has to be within micron the distance. Okay. It's interesting that you saw this, not just the formulas and theories. All right, so you have enough fun with the wire interference. Then let's continue to look into what we call multiple beam interference. Multiple beam interference. Well, previously we only have two beams, but what if we have many beams? Then that could also generate interference if there's enough coherence. Right? So think about, again, a dielectric slab like this with a thickness of D, and then you have a light source. You have a light source instant on it. Then the light is going to get reflected from the first instance, and then you have lights reflected from the back of the surface, and some will be transmitted, some will be reflected. So you have those infinite beams of interference from this setup. Okay, and this element is called epsilon. It's a very powerful optical element. Okay, and so we want to analyze the bright fringes and dark fringes of these optical elements. And in fact, all the optical cavity is one kind of epsilon, because you have the sort of reflection from surfaces and then forming some standing wave inside. Okay, and so there's an external reflection right here, and when you deal with the external reflection, you need to be careful about the additional pi phase shift in the process. For this setup, for the first beam, you have pi reflection, pi phase shift for the first beam, but now for all the others. All the others are internal reflection. Okay. So E0 is the instant light field, and T is the transmission from this, for example, air to this film, the transmission coefficient. So don't forget how we define E and R, because later you're going to look into the relationship between E and R. So we have T, that is equal to transmitted electric field, instant electric field, with R, that is equal to refracted electric field and instant electric field. Okay. But then when you have the different surfaces, for example, this is the from air to this material, then we label it as the T transmission. But when you have the transmission from this material to outside, we label with T prime. Okay, so T is the amplitude transmittance entering the film. T prime is the amplitude transmittance leaving the film. So T is equal to N1 plus NF 2N1. T prime is equal to N1 plus NF 2NF. T and T prime are different. Okay. Same thing when you have R. This is N1 plus NF, and then N1 minus NF. That is the reflectance from the film. And R prime is the reflectance from inside the film. So then you have R prime equal to N1 plus NF, and then you change this to be NF minus N1. Okay. And there's a certain relationship between R prime, T prime. So this is something that you need to keep track of. But with these definitions, we can start to calculate. We can start to calculate all the electric fields reflected from this film, or all the electric fields transmitted through this film. But for this particular one, be careful that there's a pi phase shift for this particular one. Okay, and not the rest. And then we need to keep track of the optical path difference given an instant angle. Right, is there any question about this setup? No, no question, then we start to do the, calculation of the object path difference here. Basically, we have done this calculation on the last page. We went through quite a bit of calculation for that, right? Object path difference for this ray and this ray, for this ray and this ray. The optical path difference is right here. So we have done this calculation. All right. So we just copy down the results. So we have this the optical path difference right here, and theta t is the internal angle of instance inside this beam. All right. So this is set up for this problem. Is there any question? No question. Then let's do the calculation. So this is an infinite sum. We just add for this one, we calculate the refractive field. So it's an infinite sum. We sum them all together, term by term, given by this. Right. Just cut down this and add them together. But there's a pi phase shift. So there's a minus sign at the very beginning. No question, right, teacher? Yeah, so easy. Well, this is an infinite sum with r squared less than 1 because the refracted energy cannot be larger than the incident energy. So the frequency is less than 1. All right, so this infinite sum gives you this result. When writing this, we assume that the optic path difference is integer model wavelengths. So let's set this reasonable condition. When the optic path difference between these two is differed by 2 pi. Okay. So we don't write the optical phase difference for each term. If you have to write it, then it will be exponential j2 pi, exponential j2 pi. Okay. So this is an unreasonable condition. Assume the thickness of this is the integer multiple of wavelengths. Then in the end, you need to pick this relationship. If you know this R prime, T prime, then you have this relationship. Then in the end, you find that the unreasonableness, you get nothing. All the light will just go through this piece of elements. Okay, regardless of the reflection coefficient. But this is remarkable. Why do you think it's remarkable? So let me give you some feeling. Well, this is a piece of the electron with 2 surfaces, right? And with just a single surface, and then you assume that you do some optical coating on this to get 100% reflection. Technology-wise, you can do it, right? For example, for these glasses, you can do optical coating to have 100% refraction at certain wavelengths. Nearly 100%, 99.999%. If you have a very good coating engineer, like the one in my group. But suddenly, if you add 2 surfaces, if you have 2 surfaces, just as one single surface, you get almost 100% reflection. And then you have the second surface. You change it to an optical coating. If you have 2 surfaces, the same surfaces, all right, with R, reflection is almost 100%. Turns out that you can have nothing refracted back. This is a magic. Don't you think so? For example, when you look at this glass, and then you make it 100% almost 100% reflection. But then when you do the same coating on the back of this mirror, you get 100% transmission. It's magic. Sure, do you think that this is amazing? Right? You can put some coating or some surface here to get nearly 100% reflection. But then if you do the same thing in the back of it, you get two surfaces. So you do the same thing on the back of it. So you have two surfaces. With one, you have nearly 100% reflection, but if you put the two surfaces together, you have 100% transmission. Wow. So this is magic in optics. And you have the theoretical calculation to confirm it. And indeed, experimentally, yes. That is because you store a large amount of energy here. Okay, and then you have constructed interference on reflection based on this resonant condition. So originally you can have high reflection, then with two surfaces you have anti-reflection. Amazing. So this is the calculation tells you. All right. A second case is that if you are off resonance, with the optic path difference, that is the intergeometric wavelength, and then cross the half wavelength. Then you have to be careful about the phases because of this. Because this half wavelength will introduce pi for each reflection. Because this is sort of pi phase difference, pi phase difference, pi phase difference, pi phase difference. So you need to keep track of all the phases, reflection phase. And then you end up having this result. Plus, minus, this alternating sign in this infinite sum. Okay, finish up this infinite sum calculation, you end up having this result. Well, this does not tell you much. It just tells you that with the of resonance, you have some reflection. Okay, you have some reflection. So let's calculate the intensity. That is if you absorb the intrinsic wave impedance into this calculation, you have a factor 2 here, then you end up having a result that is only if the coating here is almost 100%, would you get a reflection, 100% reflection. Okay, so imagine that you have 100% reflection here, nearly 100% reflection here, nearly 100% reflection here, and then this is off resonance. Then whatever you throw into this epsilon will be reflected back. Okay, but this is approaching. You'll never get 100% reflection. Okay, for optical coating, you can get like 99.9% reflection, but not quite 100%. So at this off resonance, the refractive intensity is always slightly less than the incident intensity at this off resonance condition. So this is the calculation that you have from this discussion. But then the next case is going to be more general. We don't set this optic path to be intergemultiple of half pi or intergemultiple of 4 wavelengths. And the calculation is going to be more general because you need to add all the phases into the calculation. And then next time we'll be discussing the general case. And now we still have 15 minutes, and I'm going to give you one quiz so that if you did not do well or your meeting exam, you can